Very good afternoon, and it's a pleasure and privilege to be presenting some of the thoughts we have on how the future of uh, energy requirements in a vessel is going to change. My name is Suresh. I represent DIVE, a global company based in Denmark. A short introduction about what DIVE is. DIVE is a company that was established in 1933. So we are close to getting to our 10th decade of existence, headquartered in Denmark, present in more than 20 countries across the world, with close to 600 employees. And the beauty is 20% of it is engineering force that's continuously working on developing new things that's required for the future. That's why we have a philosophy of improve tomorrow, because the tomorrow has to be definitely better than today. That's our belief, that's our ambition, and that's what we work for. What do we provide? We provide solutions for both land and marine-based power plants for automatic control, automation, conversion, and protection. So we almost take care of the entire electrical power flow within an energy installation. So the session was started off with the speaker before me setting very high standards about where the shipping industry is going, right? He's talking about vessels with no people on board in the time to come. So if you take the same helicopter view and see what's going on in the marine world, I think it started maybe 7, 8, 10 years ago with the aim of improving the efficiency of the ship so that we have lesser and lesser emissions. But there is a limit up to which you can reduce the emissions unless we completely change the source of fuel. So the next hunt is going on for alternate fuels. And then with the increasing interest to understand how the ship is behaving, there is a lot of exchange of information between ship and the shore. When there is a lot of connection, you also need to have cybersecurity. So the requirements for cybersecurity is on the rise. And autonomous vessels, which you heard a lot in the last 20 minutes, is only making it even more complex. So if you are going to have a vessel that's completely controlled from outside and nobody on the ship, and if someone else accesses it, you can understand what will happen. So the cybersecurity is, again, in paramount importance when we go for automated vessels, and then the big data that we get out of it, which is important to create all these digital twins, and how do we secure the high performance of the vessels. So all these also has an impact on how the ship is powered and how the control is made on the ships. So that's where DIVE comes in. So if you go back in history and start looking at where did we begin, of course we begin with wind as the force to drive with the old Viking ships. Then we came to fossil fuel because we wanted speed and efficiency. So we put a fossil fuel driven prime mover to run the vessels. And then the vessels on board had a lot of electrification, so they need to be powered up. So they were provided fossil fuel-based generation, diesel generators or LNG-based generation, which is powering the entire ship for doing the different operations required inside the ship. Then we moved from there to improving efficiency by making hybrid propulsions, where we felt that when the engine that is driving the ship has to go up and down all the time, there is a variation in the efficiency of the machine. So we started harvesting that differences and creating power out of it so that we can either take them out or put them in as necessary. So this started giving the hybrid propulsion, where you have electric assisted fossil fuel driven propulsion. But when you look forward, as you can see, like a compass, there are many options for fuels. There are a lot of development projects that are going on to demonstrate what alternate fuel can be considered to be able to have low footprint. At being a power control and energy management company, we don't bother too much about which one is going to succeed, because whatever comes out, we need to control. So this is how we are looking at this scenario, that how can we provide a control and protection system that will be agnostic to what kind of energy sources or fuel sources you will use. So that's a little bit about also the previous presentation, which talked about how quickly the hardware and software are becoming irrelevant. The speed at which they are getting phased out is so high that it's important that we build systems that can sustain longer lifespans that are required in this scenario, like vessels which live for 20, 25, 30 years. So we don't have to change everything. We should be able to upgrade them or slightly alter them so that they can run for these 25 years with minimum intervention. So here we look at the electric scheme now a little bit, not to frighten you with all the diagrams, but just to focus on how these systems have evolved. So as I said, we started with fossil fuel generation. There were simple 4 or 8 or 6 generators on board. They were running, and the propulsion was completely independent. There was no connection between propulsion engines and the onboard power, electric power generation we had. And here what we used is called as a typical alternating current or AC bus. So this system is what has been in use for last many years. Then we came with the modification of the hybrid, where we started adding a generator to the shaft and also adding a battery to store this energy. So this gave the first hybrid kind of system for the onboard power plants. And here, the power conversion became important, right? Now you are getting power from the shaft, which is not at the same level as that is at the switchboard, so you need to convert them to the right level so that you can connect them. And then it's also possible to store some of the energy in battery, because every time you convert, you also lose. You have to remember that. So minimum the conversions, maximum the efficiency. Then we go to the next level, where we started replacing the fossil fuel-driven propulsions with electric propulsion. So you started seeing motors coming on board to do the propulsion, and here the power is fed through the power converters to the motor. Now what happens? The power system on the ship is becoming more closer to propulsion, and it has to take propulsion also as a load. So the systems became a little bit more complex with electric propulsion and storage. And the storage helps people to run short distances without even an engine, right? There are a lot of ferries that operate short distances of 30, 40 minutes without any engine running on board. So this is how we got out of the fuel-based systems to electric systems. Then came the next transition, where we started mixing, because there are vessels which have been made for so many years with AC systems, but when you start bringing new energies like storage and fuel cells, then you have a DC system. How do we combine these two? Then we started working on combined AC and DC. So this is what we believe will be the transition phase, where you combine the old with the new, where combine AC and DC. And then finally, we will land probably in the more futuristic system, where it's only one DC source, where all the other sources are getting converted, or the load are getting converted to be fed by the power. So we are seeing a transition from a very conventional AC system to a combination of AC-DC to a pure DC to come in the future. And this is the challenge that a control system on board is expected to manage. And that's where DIVE's experience of more than 20, 30 years providing control systems for the marine industry comes. So we have designed a modern futuristic control platform. I don't call it a product, because like the previous speaker mentioned, we are no longer in the world where we can create products, because they get isolated, having compatibility in future, ability to run them in future get restricted. But when we get platforms, it's easy to move the hardware and the software in parallel over time, depending upon the need, without having to scrap the whole system. So what are the basic fundamentals of such platforms? The first is flexibility. Flexibility to be able to accept different energy sources. One may ask, what is the difference? This is also 2 megawatt, this is also 2 megawatt. They should be same, but it's not the same, because a response you get from a diesel generator to a response you get from a battery to a response you get from a fuel cell will be completely different. Now, are we going to use 5 different hardwares in that system to be able to control all these, or I can have just one hardware with different softwares that is needed to control this system? So this is the way we are taking design one hardware that is agnostic of application. You should be able to put any software that you need inside it so that it can run a diesel generator, or it can run a fuel cell, or it can run a battery storage. So this is the concept of flexibility we are talking about. Flexibility in electrical schemes, we saw that you might have to combine AC and DC bus bars. You might also have to have redundant bus bars. Because, for example, if you are in an autonomous vessel, and if one of the paths for electricity has failed, you have no chance. You have to continue to run the ship. So you need to have a parallel electrical path. So here, the bus bars or the bus distribution systems have to become redundant. So the control system should be also able to realize this and operate it in this way. So that's where the flexibility is very, very important. Second is open. Again, I refer to the previous presentation where you have so many elements getting connected. So we cannot have devices with fixed connection capabilities. They have to be wide open to be able to take different industrial protocols, different networks, and be able to transact data between different systems. So this is where the open system becomes very important. We also see the openness from the perspective of if I am making a product and my customer is building a system, he would also like to add something that is core knowledge to them. It's impossible for my customer to teach me or me to understand what they are doing. But I need to provide a space for them to do what they wish to do. And that's where open systems becomes more relevant because you provide programming space for the customer inside the unit so that they can develop the program and deploy it here so that they can work seamlessly with the software that is delivered by Dive along with their own software. So that's the openness we are talking about. Connected, I don't think I need to talk a lot. But security is our biggest focus when we talk about connectivity, right? I'll talk a little bit more on how the security is changing. First of all, why are we talking about it? I just try to, Google is the best friend to know if you don't know something, right? If you ask Google, this is what it says. It says that there's so many attacks that are happening on vessels, right? You can see 23,000 malware detections were made. 178 ransom attacks were done. 50 plus billion firewall events, either intentional or unintentional breakages have happened, right? And 14.8 billion alerts in a short span of time, right? This is the threat that we are seeing. It could be intentional, it could be unintentional, no matter. The system needs to be protected. How is it being done? When it is intentional, it is done either by people on site, if people are visiting the vessel to update, maintain, or reconfigure things, they can also do this. Then you have malwares. You have a lot of IoT connected devices on the ship. The malwares can be sent through them. Or a purposeful attack by some experts. So there are different levels of attacks that can happen on a ship. So what's the standard say? The standard clearly says that the system should be defined to say what level of attack it can withstand, right? At what level of attack it can protect the system. So we have level 1, 2, 3, 4, as per IEC 62443. And we also have the maturity levels, right? The CMM levels, which says that is this system just designed for one, or we are continuously building, improving, and maintaining it so that every time you have seen a failure, you address it and improve your protection system. And this requires, as it was also mentioned, that a number of updates will be needed. You cannot update a system on 2 years, you don't go to the ship. You need to update. So updates on the air, updates over the servers, all this will be necessary, but with protection. And that's where the certifying agencies come into picture, and we were fortunate to work in the first level of implementation last year and get approvals from different class societies to ensure that the products have the built-in cybersecurity to the level needed. The third important thing that we saw is power conversion, right? Conversion, as I said, every time you convert, you also lose some power. So the efficiency becomes critical. The second is the thermal capacity of the unit, right? How much I can load the unit without damaging it for a given ambient performance or temperature. Then you talk about how compact it is, because ships don't have lot of space, right? They are actually fighting for space. So the more compact your system can be, then it becomes better for the design of the ship. And then weight. If given a choice between would you like to carry 100 kilos more of items that can produce money for the vessel owner compared to 100 kilo of capital equipment just producing power, The answer is quite simple. The vessel owner would like to make more money. So the systems have to be lesser and lesser in weight. So from all these considerations, when DIVE decided to get into this power conversion field, we chose the technology of silicon carbide, which brings all these benefits to the power conversion. First of all, why the losses are less. If you go into the physics and the way the silicon carbide works, here you can see the comparison between a general IGBT and a silicon carbide MOSFET. The loss levels are so low that it allows to have a high level of efficiency, right? So this is a material property combined with the engineering skill that's able to give us low losses, which also makes the size of the equipment smaller, which in turn reduces the weight of the equipment. Then we talk about efficiency. Efficiency is not just at one point, because the ship in real time operates at different load levels, depend upon how harsh the sea is or how soft the ocean is, right? So we cannot expect it to always operate at X percentage of the load. So when the loads are varying, are your efficiency capable of staying at the same level? And this is what we also get out of SIC, where the efficiency stays high, as high as 98.4% across different loads that can be witnessed in the ship. Then we talk about how do we reduce the size and the weight. If you see a power converter, it's not the electronics that is the heaviest element inside a power converter. It's all the magnetics around the power conversion, right? We have filters with inductors and capacitors that are connected. And here, silicon carbide has the uniqueness of being able to switch at high frequency. We can take the switching frequency to 60, 70 kilohertz. So what happens when you do from low frequency to high frequency? We just explained it by a cup. Like if you have a big cup and you're filling coffee, it takes more time. If you take a small cup and fill coffee, it's much faster. So it's like that. The higher the frequency, the faster the fill rates are. And that's why we are able to reduce, right, the amount of electromagnetics needed inside the system. So that results in enormous saving, both in terms of weight and also in terms of volume. A typical example, a 1 megawatt IGBT-based system can have as high as 900 kilograms of extra magnetics, whereas if you look at the SiC, silicon carbide-based systems, it can have only 1/10 of this size. So that's the reduction that you get in weight, and also in volume, you get a reduction of nearly 40%. So this is the advantage we are trying to deliver to the marine world, which is actually hard-pressed on the sizes. So what does a new energy system need in total, right? One, intelligent energy control with open, flexible, connected controllers. Two, a cyber-safe system so that it is compliant and continuously improved. Now, this is very important because the smarter the protectors are, the even smarter are the attackers, right? Every time we increase the security level, they also try to raise their level. So this is a never-ending war that we are getting into. So we should be in a position to continuously improve these systems. And then power conversions, that becomes compact, efficient, and high performance. And this is exactly what we are trying to make as a combination so that we will make the future vessels, no matter what fuel they select, hydrogen, ammonia, depending upon what's able to provide in the infrastructure to deliver those fuels, the safety on the vessels, that's also important, depending upon what is giving the highest level of safety. Any choice of fuel made, we as DIVE should be able to provide a control system on power conversion that can completely take care of the future requirements of the energy systems. So that's what I had to present. Thank you for your patient hearing. And if you have any questions, I think we'll have a session. Also, we have a booth here. You are welcome to visit us and meet our colleagues who can help you with the possible information that we have. Thank you. Kamsahamnida.